Hi. Today's tutorial is on section 4.1, Rules of Exponents. And I want to stress one major thing about this, and you can see it right up here. Exponents have more meaning than they have value. That's going to be an important theme that we work with over and over in this discussion today, in this tutorial, is the meaning of the exponents, not so much the value. What does an exponent mean? As a quick reminder, if we have something like 5 to the third power, we call this 5 the base, and this 3 is called the exponent. And we want to look at not the numerical value of 3 as if we're doing anything special with 3 and 5, but instead we want to really treat this as something like this: 5 to the 3, meaning 3 factors of 5. 3 factors of 5. Also interpreted as 5 times 5 times 5. If we multiplied this all the way out, we'd find that it's 125, but the real key to this is right here: 3 factors of 5. 5 times 5 times 5. Notice what we didn't get is something like 15. 5 times 3 is 15. Clearly this is not 15. That's a lot larger than 15. So it's not a multiplying 5 times 3. That's why I don't want you to think of that 3 really as the value 3, but look at the meaning of the exponent. 3 factors of 5. 5 times 5 times 5. Okay, and that's how we'll be working with our rules of exponents today, is based on the idea that exponents have more meaning than they have value. So I'll be referring to this quite a bit today. All right, I'd like to first start, since as I do normally, I'm going to be going over examples from the textbook. I am expecting that you will still do the reading before or after, maybe during this presentation. And so some of the things that I mentioned in the discussion today, now I think this might be, some of it's in the book, but not all of it, but things that I mentioned today will be from the examples and not necessarily all of the information from the textbook, and that's why it's important that you read the text. Okay? All right. Well, let's see. Let me start fresh here with example 1, and we're simply asked to consider in example 1. Oh, by the way, this is on page 4.1-2. We're simply asked to consider to state the meaning of each of the following. So a simple example would be part A says 2 to the 5th power, or 2 to the 5th. And what does it mean? It means, just like I was saying before, 5 factors of 2. And that means 2 times 2 times 2 times 2 times 2. That has a value. We could multiply it out. If you multiply 2 times 2 is 4, times 2 again is 8. Notice that we're doubling everything. Times 2 is 16, times 2 is 32. And so this answer is 32. Okay? And that's what you need to do with the rest of example 1. What we do find out is, and there's a couple of rules that follow directly after this, and I will mention these, is that 0 to any power, like say the 4th power, is going to equal 0, because that's 0 times 0 times 0 times 0. It's equal to 0. 4 factors of 0. It's not going anywhere. It's still 0. Same is true for 1. If we had 1 to the 4th, 1 times 1 times 1 times 1. 4 factors of 1, but it's not equal to 4. It's equal to 1 times 1 is 1, times 1 again is 1, times 1 again is 1. It will equal 1. And that's true no matter what the power of 1 is, or what the exponent for 1 or 0. Notice what they equal. Okay, well, those are a couple rules that you'll find on that page. Let me, I'm not going to go over example 2. Example 2 is really pretty self-explanatory. So the next key is going to be working with the product rule. And I'm going to erase everything here. But recall that a product equals, or means, I'll put it this way with 3 bar equal sign, means multiplication. And what we're going to be looking at are things like 2 to the 3rd power times maybe 2 to the 5th power. 2 to the 3rd times 2 to the 5th. And looking at the did I ever mention to you that exponents have more meaning than they have value? You ever heard that before? Well, I thought so. So if we look at the meaning of 2 to the 3rd times 2 to the 5th, it means that we have 3 factors of 2, which means 2 multiplied together, 2 times 2 times 2. Let me write that down. Whoops. 2 times 2 times 2 times. And we have 5 factors of 2. 5 factors of 2. That's what this means, right? So let me write those factors down. 2 times 2 times 2 times 2 times 2. So I see the 3 factors of 2, and I see 5 more factors of 2. A total of how many factors of 2? That's right, 8 factors of 2. So we can abbreviate that as 2 to the 8th power, because 8 factors of 2. That's the meaning of the exponent, 8 factors of 2. Yeah, we can also get a value. 2 to the 3rd power is itself equal to 8, and 2 to the 5th power, we saw in a moment ago, is 32. And if we multiply those two together, let's see, 2 times 8 is 16, 6 carry the 1, 256 is the 8th power of 2. But really right now, I want to concentrate on how the exponents are going to come out, especially because we won't be dealing so much with numerical bases. We'll be dealing with variable bases like x to the power, x to the 3rd times x to the 5th. What would that be if it were x to the 3rd times x to the 5th? X to the 5th. Well, 3 factors of x, and, because we're still multiplying here, 5 more factors of x. So since product means multiplication, in fact, factors means multiplication. So putting those ideas together, when we talk about the number of factors, here are 3 factors of 2 times 5 factors of 2. Notice that it's multiplication all the way across. So a total of 8 factors of 2. And same thing here. 3 factors of x and 5 more factors of x. Multiplied together, that is a total of 8 factors of x. Well, from this idea that exponents have more meaning than they have value, we develop over here how we can expand these values to get a new set of factors of 2 or sometimes of x. And what we recognize is that we end up with the same base, which is 2 in each case, but a new exponent based on the idea that we actually had to add these values together. We had to actually add 3 and 5 together. So that brings up the product rule, which is in your textbook, and I'll go ahead and mention it right here. Product rule is that if we have x to the a power times x to the b power, that's x to the a plus b. And we see that right up here in this example. If we just add 3 plus 5, that exponent, we get x to the 8th. So the exercises here help you understand it for yourself beyond just me telling you. Really, it's helpful for you to understand it yourself. And so that's what some of the exercises in the textbook are about, is you understanding what this means, what this expansion means. What this expansion here means, and how we can put them together, and the idea that the product rule allows us, as long as these bases are the same, that when we multiply, remember multiplication means factors, exponents means factors also, that we just have a combined total number of factors. Same base hasn't changed. This 2 never changed. It's always 2 times 2 times 2 times 2 times whatever it was. We only changed it when we found its value eventually. But, if it were x, the value would never change. It would just be 8 factors of x, all multiplied together. Anyway, we add those exponents. Add the exponents. Okay? So, with that in mind, we'll do an example 4 problem. I'll erase everything here, and I'm now going to do, this is found on page 6, so 4.1-6, example 4, A. 4A says we have b to the 3rd power times b squared. And it's simply a matter of saying that this is equal to b to the 3 plus 2. Did I ever tell you that exponents have more meaning than they have value? I think I did. And so the meaning here is 3 factors of b times 2 more factors of b, a total of 5 factors of b. I made you wait for that one. You knew the answer anyway. Part B says y to the 3rd times y to the 4th. That's y to the 3 plus 4. That's the meaning of the exponents. That's y to the 7th. C is a little bit different, not much. The same idea. It says x to the 5th times x. What's different about it, though, is that each of these has an exponent. The first term has an exponent of 5. The second term has an exponent, but we don't see it. And this is the idea that everything has an exponent, and if we don't see it, it's to the power of 1. So let me go ahead and write in the power 1 here, so that when we evaluate this, that's x to the 5 plus 1, x to the 6th. Okay? That's an important thing to recognize. And that will actually come into play quite a bit, this idea that even if we don't see the exponent, there's still one there, and we can put it there whenever we need to. Okay? All right. The 0 power rule. I'm going to erase all this. And I'm looking on page 4.1-7. And this is the 0 power rule. This is more than just an example. I want to describe this and explain it a little bit. This idea is a challenging idea. And more than anything, in the beginning, you just have to take it on faith that what I tell you is true. And I hope that you believe me anyway, but this one is a hard one to grasp and fully understand. And so maybe instead of trying to fully understand it, it's best to just accept it. It is true. It is undoubtedly true. Believe it or not, x to the 0 power equals 1. X to the 0 power. Y to the 0 power equals 1. 2 to the 0 power equals 1. Negative 9 to the 0 power equals 1. 15xy, all raised to the 0 power, equals 1. It doesn't equal an exponent of 1. It doesn't equal like to the 1st power here, or y to the first, it equals the number 1. And we got to remember, exponents have more meaning than they have value. So what we have to recognize is the meaning of this. This means that there are 0 factors of x. And when there are 0 factors of something, it's the same as saying that there is the number 1. Not one factor of that value, just the number 1. And so this is a hard concept to understand. It might be easy to memorize, but even then, sometimes it's easy to forget too. So do your best to understand it with the examples that I have here. Also, take it on faith, and yes, memorize it, but try to get to the point where you really know it. There are a number of ways that I can represent this, but I'm going to show you 2 today. One is on this page 4.1-7, and excuse me just a moment, I have to look over here. There it is. At the bottom of that page, I write this: a to the 4th times a to the 0. I write that. Well, let's think about this for just a moment. A to the 4th times a to the 0. We have this product rule that says, hey, if you have the same base, a, then we can add the exponents, 4 plus 0. And in adding the exponents, well, let's see, what is 4 plus 0? That's right, it's just 4. Well, that's kind of interesting. Here we started with a to the 4th, and we multiplied it times a to the 0, and we ended up with a to the 4th. What do you think that means about a to the 0? Well, think of this for a moment. A to the 4th times what equals a to the 4th? A to the 4th times something equals a to... What's that you say? Times 1? Exactly. A to the 4th times 1. Anything times 1 equals itself. So if a to the 4th times a to the 0 equals a to the 4th, that suggests that these two have the same value. A to the 0 equals 1. This is the first way for me to demonstrate that this 0 power, and when we have any base raised to the 0 power, it's equal to 1. Oh, by the way, there is one exception to all that. 0 to the 0 power like that is undefined. We can never have 0 to the 0 power. And the basic reason is this. We've been saying here that anything raised to the 0 power is 1, but we also earlier mentioned that 0 to any power, like 0 to the 5th power, equals 0. And so you might say, well, wait a minute. 0 to a power. Should it be 1 or should it be 0? When we have what's called an ambiguity, where it can be more than one thing, in mathematics we say not allowed, we say it's undefined. So for 0 is the only base that we can't have to a 0 power, but any other power, any other number works, whether it be a variable or a positive number or a negative number, even a fraction. That's one thing I was trying to remember what it was I wanted to mention also. 3/4 to 0 power, still just 1. Okay? So that's an important idea, and I'm going to come back to that in just a little bit. And so I won't go over example 5. This explanation that I was giving here was basically related to example 5. So you can read through that. And it's also true for example 6. I'll let you read through that. Now we're going to get to a rule called the quotient rule.